All right, let's get started. My name is David Waltzman, and I am a Senior Simulation Product Specialist with GoEngineer. And the topic of today's session is going to be on fluid optimization, paving the way to fracking season. What is fracking? A lot of you may know because you're here. Maybe you're looking to learn something new, so let's just go over the basics. Hydraulic fracturing, aka fracking, is the fracturing of rock by a pressurized liquid. Water is typically mixed with sand or some other chemicals and then injected through a well bore. This is just another word for well, at high pressure to create small fractures. Typically, these are around a millimeter or so in diameter. Right, so in this image here, we just have a picture of a well. And fracking's gotten a lot of attention lately in the news, right? So is fracking new? Are we experimenting with something we don't really understand? Well, hydraulic fracturing's been around for decades, but now it's becoming more widespread. And the reason for that is traditionally it was just done once over the life of the well to enhance the productivity. But now the trend is to get everything we can from the wells that we have, so the fracking may be done multiple times as the production declines. We have just some statistics about fracking. All right, so one of the ones we're going to focus on today is the amount of water that's used for the fracking process. So for each well, we have 200 trucks of water that are going to come in to be injected down. And that's going to be mixed with sand and other chemicals. We call these proppants, right? And the pressure from all these proppants is going to cause the rock around the pipe to crack. And when it does that, the gas is released and then flows upstream through the well and is collected. While that all sounds good and dandy, there are some risks that come with this, and that is groundwater contamination and air quality degradation. Groundwater is pretty self-explanatory, right? It's seeping through other layers, and chemicals get in the water supply. And air quality would be it coming all the way to the surface. Right. Nationally, we have anywhere up to 140 billion gallons of water that are used for fracking every year. Right. And just in one individual well, we can have as much as 4 million pounds of proppants used. And of all that fluid that's inside, up to 2% could be various chemicals. Right? And just again, I want to emphasize the volume of water and how much is used. Right? That's enough for the consumption of 40 to 80 cities. All right, so the primary goal and challenge that we want to look at in this series is the water delivery system from the trucks. Right, so over 200 water trucks are used for each well. So it's critical to explore multiple designs of the valves to distribute the water, optimize them for efficient delivery of the fluid, make sure that they're going to last. Right. So, just a thought out in the clouds. If only there was a tool that allowed us to design intelligently and optimize for fluids. Right. So you may have stumbled before upon SOLIDWORKS flow simulation. That's our CFD tool that we represent at GoEngineer. It's a general purpose fluid flow and heat transfer simulation tool. There's several facets to it, though, that make it widely applicable and useful in our scenario here. The first major benefit of it is that it's fully integrated with SOLIDWORKS 3D CAD. So if you're already using SOLIDWORKS for your mechanical design, this is just more picks and clicks in the same environment. We can simulate the performance of our products, with fluid flow as well as stress with our FEA tool, SOLIDWORKS simulation. And again, all have that under one house, same person, same environment. We can look at internal as well as external flows. Right, so internal flows would be inside of a watertight volume, whereas external would be the flow over an object. We have the capabilities to look at incompressible as well as compressible fluids. So if you think about water as incompressible and air as a compressible fluid, those are the most common. We could also look at non-Newtonian fluids, right? Think about blood or honey. Our solvers also can address laminar, turbulent, and transitional flows. All right, and we have a great automatic setting that looks at the K-epsilon transition to turbulence and can do a lot of the work for you, so you don't have to have a predetermined idea of how the simulation is going to run. SOLIDWORKS Flow Simulation also has a great heat transfer tool. Right, so we're doing physical dynamics for flows, but also heat transfer. And the reason why it's such an excellent tool is that we're modeling the air or the fluid around it, so our convection is much more accurate than in an FEA tool where you're only modeling the solid. Finally, everything's coupled with SOLIDWORKS simulation. So if you're looking to get stress calculations and the displacement from our flows, we can import non-uniform pressure and temperature distributions. Right, so traditionally, CFD is only used by CFD experts. Right, so on the left, we had our mechanical engineers that's working in their CAD system, making a great product, and then they throw it over the wall to the CFD analyst. Right, this is traditionally, PhD, writing code, and exclusively does that. The problem with this is that there's a delay, right? So the mechanical engineer designs something, it goes off for analysis. Maybe the results come back, maybe they don't, maybe the design's finalized already. But either way, you're not able to explore all the different possibilities that you would if everything was handled on one side of the house. So we're not proposing that we replace our CFD analysts. They're still important. But what we would like to encourage is that in the design phase, that the mechanical engineers start incorporating CFD tools so that they can create better designs. There are 7 unique technologies that enable concurrent CFD. All right, so concurrent, I mean designing and simulating and iterating. All right, so we have an excellent what-if analysis that we'll be looking into in our case study here. We have an intuitive interface, again, same great UI that we're used to in SOLIDWORKS. We have automated boundary Cartesian meshing. So what does that mean? That when we create our mesh, we don't have to worry about all the surfaces. Let's say we have a pipe, we're simulating it. SOLIDWORKS uses partial cell technology to address all those interfaces and make sure that we're modeling the boundaries sufficiently. We have a turbulence model, as mentioned, that K-epsilon model, transition to turbulence. So we're able to intelligently address that. And as far as solution convergence, we have some very simple tools to choose that for you. And of course, you could dive deeper, but we don't want to exclude people from using it, and we want to enable them to use it faster and more often. So why is all this so important? Traditionally, if you go through concept to manufacture, you start off maybe with a hand drawing or a primitive SOLIDWORKS model. You get into a more advanced conceptual model, you go through several different options, and your group decides on the detailed design that they'd like to proceed with. Right? Then we do analysis, move forward with publications, right? And then manufacture. But what we propose is that you integrate CFD into those first 3 steps. So now your concept, modeling, and detailed design all are iterating and done concurrently with those steps. This results in a shorter time to market and an increased quality of your product. All right, so this allows us to innovate more often. Again, it explores what-if scenarios. Maybe instead of looking at 2 situations, now you're exploring 15. Right? So just working more effectively. So let's focus more on that what-if analysis capability. So in SOLIDWORKS Flow Simulation, we call that our parametric study. This allows us to grab a model dimension or a flow parameter, such as a flow rate or a temperature, and analyze all these different scenarios. Once we create all these different scenarios, we can clone our studies, so our flow simulation setup, to each of those situations. We don't have to create it each time. All right, so this is using 3D configurations from SOLIDWORks. Okay. This is great, and in 2014 you could selectively choose which scenarios you want to create a configuration from so that your file is not flooded with 100 different scenarios. So the benefits of what-if analysis. You said, well, I can just enter those manually in there. Why should I do it all at once? Well, when you set up the parameters and let it run, you can let it go overnight or on the weekend and investigate a lot more than you would have before. Right? The product we're going to be looking at is a globe valve. Right? So we have our water on the truck. It needs to get out. So there's going to be a pressure drop across this valve. Right? There's going to be a static pressure on one end, right, of the fluid coming out, and we want to do some investigations to optimize our design. All right, so our challenge is we're going to assume that the fluid is water, right, and that makes sense. It's coming out of that water truck. We're going to say that it's coming in at 2 bar and coming out at 1 bar. So there's a 1 bar pressure drop. And we want to look at volume flow rate, valve seat force, and our valve coefficient. The objective of investigating all these different scenarios is to minimize the valve seat force. And so as far as setup, SOLIDWORKS Flow Simulation has an excellent wizard for setting up our simulation. Usually wizards are something that as engineers we shy away from because we're better than that. But in flow simulation, this is really the most effective way to get your project going. The first step is to choose if we have an internal or external analysis. So we'll choose internal, and we have a box next to it for excluding cavities without flow conditions. This is a great time saver because there are some volumes of our globe valve that don't have flow going through it. It's just a closed off volume, and we don't need to analyze that. If we were to investigate thermal effects, we can add heat conduction and solids to our model. And if we just wanted to look at, let's say our product was in a vacuum and there was no air at all, we could have conduction only in solids. We could also choose to activate radiation. The reason why that's not activated by default is that radiation is a fourth order equation, right? Adds a lot more solve time. The time-dependent option brings transient capabilities, right? So now we're able to model in physical time. Gravity is excellent if you're studying natural convection, right? That all has to do with buoyancy and how the air is shifted. And then rotation is for rotating regions in our study. So all the solids in SOLIDWORKS Flow Simulation are rigid and do not move or rotate, right? So they don't translate or rotate. So a very common problem that we solve, though, is something like a fan or a turbine spinning, right? So what we can do is define rotating regions of fluid in our model around those objects and get the same relative effect. So moving on from there, we need to choose what fluids we're analyzing. We could have multiple. In this case, we're just studying water. But we have gases, liquids, non-Newtonian liquids, real gases, steam. Steam would be, if you're analyzing humidity in your model, you'd probably want to have steam in there. And then at the bottom of the screen, we have our flow type. So the default is that transition one. But if you know you're just studying laminar equations, then you can set that as well. So as far as our setup goes, after the wizard, we need to set up our boundary conditions. Right, so I was saying before that for an internal analysis, we need to have a watertight volume. That means the inlet and outlet are closed off with lids. And at these lids, we need to specify a velocity, a volume flow rate, or mass flow rate. In this case, we're using a static pressure. Right? So we define it on these faces where the openings previously were. And then we set goals for our simulation. Goals serve a dual purpose. One is it reports values that we can read at the end of the simulation. So if we're interested in the average velocity or the inlet or outlet pressure, we're able to read that right away. The other purpose is for convergence control. Right? So when SOLIDWORKS flow simulation is running, there's so many variables at every point in space that we want to choose which ones are important to us so that we could have a reasonable solve time. The last option is for equation goals. And the reason why we use those here, those are all the flags with sigmas, is that we're able to calculate equations so that we don't have to get an output and then open up Excel or our other calculator and figure out what the GPM is or what the valve coefficient is. We'll have SOLIDWORKS calculate it for us internally. Running the simulation, we can choose to run locally on our computer or on any other computer with SOLIDWORKS flow simulation. Another great capability is that we can choose how many CPUs that we want to run on, how many processors. So on my computer, I have a quad-core processor, right? And each core has 2 threads, or 2 CPUs. So I could run the simulation on all 8 CPUs, or I can choose to only run it on 4, or only on 2. Right? So we can run 2 simulations at a time. Using our batch results, we can prioritize the order that all of those simulations are run. Our solver is completely multi-threaded, right? So here you see an example with all 8 cores, or sorry, all 8 threads going to work, right? The amount of memory isn't maxed out because the memory depends on the size of the problem that you're analyzing, right? How many cells are in it. But CPU determines the speed. As far as post-processing goes, we have quite a few choices. One of the most popular ones is probably the section plot. Right? So you're able to take any slice in 3D space and look at the quantities there. So that could be pressure or velocity, temperature. We also have flow trajectories that model the streamlines, right, of our flow. So you choose a surface that you're interested in, and then how many trajectories across that surface you want to model. We can also generate surface plots, like in the bottom right there, and that looks at all the surfaces where there's a solid and fluid interface and creates a plot. We can also view these results in eDrawings, which is a free viewer and downloadable online. All you need is an email address. And that, again, allows someone to look at the 3D model and simulation results without having a seat of SOLIDWORKS. On the far right, we have some curves that are generated from our goals. And so we have velocity, force, valve coefficient, GPM. And so we can choose to view these in SOLIDWORKS or export them to Excel for further processing. You get all the raw data in Excel, and then you can manipulate it however you like. Let's talk more about those what-if scenarios. All right, so in this case here, I'm interested in ranging my inlet pressure from 2 bar to 5 bar. I'm also interested in changing the temperature from 20 to 50 degrees Celsius. And so for each of these models, I'm going to vary if my valve is fully open, if it's 3/4 open, half open, or 1/4 open. So let's set up our parametric study. First step in that study is to define input variables. So here I'll say that my total pressure, right, is initially 2 bar, but I want to try values of 2, 3, 4, and 5. So here I enter discrete values for those, but I could also choose a range with a step size, and SOLIDWORKS will figure out those values. So whichever way facilitates your needs the best. We're also varying our temperature, right, between 20, 30, 40, and 50 degrees. Okay. The next step after that is to select what output parameters you're interested in. So here we're interested in the valve seat force. So SOLIDWORKS ran through this. It created 15 studies here looking at the valve coefficient. And we can see the trend, right? So scenario 1 was 2 bar at 20 degrees. And then scenario 2 was 2 bar at 30 degrees, 9.3, 2 at 40, and 2 at 50. And then it resets at the higher pressure, 3 bar with 20 degrees, 3 bar with 30 degrees, and steps through all the scenarios that we defined. So it's pretty clear here what the trend is. So we've seen how simple it is to set up a simulation, our advanced visualization techniques, and we have investigated multiple what-if scenarios. Now let's explore the design optimization route. So for my optimization, I'd like to find what valve seat position will ensure a force of 500 newtons on my valve seat, right, with a tolerance of plus or minus 10 newtons. Okay. So the difference with the design optimization is that you're choosing one parameter that you want to optimize instead of investigating a whole slew of them. All right, so here we're choosing a sketch dimension from our model, right, and then specifying a range for that dimension. So we're saying from 0.019 to 0.098. Notice we're not doing discrete values like before or saying the number. And the reason for that is SOLIDWORKS is going to bounce around these through binary refinement until it hits our target. So our target output parameter is again that valve seat force, and here we see how we define that 500 plus or minus 10. So after cooking, it took 8 iterations for it to converge. All right, so it started off the valve seat force of 150 newtons. All right, so that was at the max dimension. So that means as far open as we would allow SOLIDWORKS to be. And then it went to the minimum point and saw a value of over 800, right? And that's because we're choking the flow there. There's a very small opening for the pressure drop, right? So then it bounces around until we get within 495.7, which is inside of our plus or minus 10 range. And at that point, SOLIDWORKS knows to end the simulation. So here's a plot of what those results look like. So again, we start off around 150, shoot up to 800, go down to a little over 300. Then we come up to just under 5, but not within tolerance. We keep bouncing around until, again, at iteration 8, we hit gold. All right, so in summary, we saw that the simulation was pretty easy to learn and to use. Right, in terms of advanced visualization, we could view those flow trajectories, surface plots, and cut plots, as well as use e-drawings outside of SOLIDWORKS to view our results. We investigated multiple what-if scenarios to reduce physical testing time, and then optimize our design to find the optimal force on our valve. Here I'd like to close with an industry report from Aberdeen, who found that there was a 28% decrease in development time after companies implemented CFD. Right? This is CFD in general as a topic. 89% of products in the survey met release dates, 90% met quality targets, 87% met cost targets. We also saw a 24% reduction in product cost time. Right? So zeroing in, focusing on our topic from today about these what-if scenarios and optimization, they found that 37% of engineers that were using CFD said the product would work, but probably not be optimized for cost, quality, performance if they were not using CFD anymore. 34% of them said that fewer scenarios would be tested because physical tests are not possible for all conditions. Again, when not using CFD. So these are the same brilliant engineering teams, but 1 in 3 says that it would work better and they would try out more scenarios if they had tools that allowed them to do so with ease. So that's really the strength of SOLIDWORKS flow simulation and how we would like it to be used out in the field. So that's the presentation that I have prepared for you. We're at 12:30 now, and we'll open up for questions. All right, then I'd like to say thank you for calling in today. I've enjoyed delivering the presentation. I hope that the content was valuable for you. Again, if you have suggestions for future content, feel free to send an email to your local sales rep or engineer or myself, and we'd be glad to address it in the future. So thank you again, and have a nice day.